While my presentation is coming up, I'd like to say that it's a great honour to be here as an international speaker from Australia at this important meeting. Myself and our research team in quantum computing in Australia have been now working in collaboration with the US government quantum computing program now for almost a decade, and so it is indeed an honour to be here at this forum. So I want to begin, first of all, by giving a quick summary of the key application areas of quantum information science. So this talk is somewhat a departure from the three preceding talks, in that the applications for quantum information science, while there are some that are already in the realm of usability today, many of them are some decades away. But as I hope I'll be able to convince you during this talk, the implications for the decades to come could be very profound indeed. So the quantum information science covers two main areas. The first is quantum communications, which I'll describe in a moment, and the other is quantum computing. So effectively we're talking about information technologies that utilise quantum mechanics to provide new disruptive technologies. So if I just look at the four key application areas of interest to this area, the first one is in the area of data security. So quantum communication systems offer perfectly secure communications with obvious applications in areas of security, secure information transfer. Quantum computing has its main applications in decryption and in supercomputing. In the area of decryption, quantum computers offer the ability to crack existing public key encryption codes in seconds, whereas conventional computers would take potentially millions of years or the life of the universe to crack very large codes. So this obviously has very important implications for national security. Quantum computing also offers the ability to do enormously parallel computations, which are important for data simulation and modelling, very similar to what we've just seen in the previous talk. The need for intense computing power obviously has an enormous number of applications. I've just listed some of these here, including bioinformatics and so on. And finally, while it's not a direct application of quantum information per se, the technologies that are being developed, the nanotechnologies and single photon technologies being developed in quantum information science, have a number of other spin-off applications, one of which I'll touch upon is in the semiconductor area, in particular the development of advanced integrated circuits and sensors. So this talk is going to be necessarily quite high level because some of the concepts are extremely detailed. For those of you in the audience who have a deeper base knowledge of quantum information, I apologise that this is going to be at a high level, but I'd like to try and communicate the key concepts to as broad an audience as possible here. So I'm going to begin by giving an overview of what the key conceptual aspects of quantum computing and quantum communications are. I'll then talk about the underpinning technologies that are in play to try to make quantum computing a reality, and these involve single atom and single photon nanotechnologies. So it's really pushing nanotechnology right to the limits of manufacturing with individual atoms, and I'll show some of the experimental results that have been achieved in this area. I'll then give more detail on some of those applications and give you an idea of the timelines for those applications. And finally, I'll finish with a visualization of what a quantum computer of the future may actually look like. So, as many of you are probably aware, the semiconductor industry has been following a path for the last 4 to 5 decades, which is well described by Moore's law, developed by Gordon Moore, who founded Intel, who noted that the size of transistors could be reduced roughly by a factor of 2 roughly every 18 months. And this has allowed us to, over the past decades, pack more and more transistors onto an individual computer chip. What that means is that the size scales for each transistor has been reducing now to the nanometer level, so that the feature sizes on an existing existing Pentium processor, for example, are now of order 50 nanometers or so. And if the roadmap were to continue, then within the next 20 years, the size of individual transistors will be approaching the size of individual atoms. Now, existing CMOS technology simply cannot operate at those length scales, and well before those length scales are reached, the other problem that's related is the power density on the chip. If we were to continue using the existing MOSFET transistors that are used on existing Pentiums and reduce the size down by a factor of 100, then the power density on the surface of those chips will be equivalent to the power density in a nuclear reactor. So the silicon is simply going to melt well before we reach that time. So one of the ways in which this has been worked around is by simply multiplying the number of chips running in parallel, but of course then we lose the benefits of the miniaturization and the communication speeds and so on. So the existing industry is facing serious challenges, and quantum computing has been identified as a possible saviour ultimately for the field. So what's the main difference between a conventional computer and a quantum computer? Just like a conventional computer where information is stored in bits of 0 or 1, corresponding to a transistor being on or off, a current flowing or not flowing. In a quantum computer, the idea is to encode this digital information in the quantum states of some physical system. And there are a number of different physical systems that are currently being explored, and I'll talk about those in just a moment. But to give the easiest example is just two different energy levels within an atom. So we could consider the ground state of the atom to be a logical 0 state, and perhaps the first excited state to be a logical 1 state. And we want to manipulate those states within the atom, perhaps by using laser beams, photons, etc. And of course we also need to be able to read out the states of that atom. Another important physical implementation or storage scheme for quantum information is the spin of electrons or of nuclei. The scheme that I'll be talking about most in this talk is encoding information on the spin of an electron. An electron has only two possible spin states in a magnetic field. That one is having its angular momentum parallel with the magnetic field, and the other is anti-parallel. And in this way we can store information, quantum information that has two very clear distinct states. So if that was all there was to quantum computing, no one would be bothered, because it's an incredibly difficult task to try to encode information and read out the states of individual atoms or subatomic particles. But the power comes from the fact that in quantum mechanics we can actually produce physical superpositions of states. In other words, a spin on an electron can actually be in two parallel states at once. It can be in both spin down and spin up. And this superposition allows us to store incredible amounts of information onto one piece of one physical system. So let me give you a particular example which is often quoted to explain the benefits of quantum information processing. Imagine a byte of information that has 300 bits. Okay, that's a slightly unusual number. I'll explain why this particular one's been chosen. But just as we can have a 32-bit or 64-bit byte, imagine a 300-bit byte. At the moment, that could easily be done in a conventional computer if we wanted to. There's no particular benefit in going to such a large byte size. And so, for example, the array of bits could be, as shown here, some particular array. And the possible states of that 300-bit byte would be 2 raised to the power of 300. And so this is the reason we've chosen 300 here, because that's roughly the number of atoms in the universe, an incredibly large number, obviously. Now, if we had a conventional computer, such as, for example, the most powerful computer available at the moment, Blue Gene, which can perform 10 to the 15 operations per second, it would take 10 to the 78 years, which is well beyond the lifetime of the universe, to just look at each one of those states. The benefit of a quantum computer is that because each one of the bits can be both 0 and 1 at the same time, If we put each one of these bits into a superposition state, then this single 300-bit byte can store all of those 2 raised to the power of 300 possible integers at the one time. And then, so we can then compute with these and perform important operations. The concept of quantum computing was first conceived by Richard Feynman, who received the Nobel Prize for quantum electrodynamics, but he came up with many other great ideas, and one was in a series of lectures on computing, prophesized the idea of actually using individual atoms and their quantum states to do computing. The title of his talk was "There's Plenty of Room at the Bottom," and at the time there was no idea of how to actually develop algorithms for this, and it took a computer scientist at Bell Labs, Peter Shaw, in 1994 to show that if one had quantum states, it would be possible to run an algorithm to perform a very important function, which is to factorize a large composite number into 2 prime numbers. Now, for anyone who's familiar with public key encryption or RSA encryption, that is effectively the key to public key encryption, the ability to factorize a large composite, and the fact that a quantum computer could perform an operation in seconds that would take thousands or millions of years was really one of the key drivers for intense research in quantum computing. So just back briefly to quantum communications, I mentioned this is the technology of sending individual photons between 2 sources, and in quantum communications what is done is that the sender actually begins with 2 separate photons. These 2 photons are put into what's called an entangled state. One of the photons is then sent to the recipient, Alice here, while the other photon is held back by the sender. This is just one possible protocol. The key thing about quantum communications, which makes it secure, is that if there is an eavesdropper looking at the photon that's sent to Alice, then through the entanglement between this photon and this photon, there are 2 steps. First, Bob will actually see that the wire has been tapped, and secondly, the information is destroyed anyway. So quantum information provides the only known perfectly secure form of information transfer between 2 points. So back to quantum computing, and I should mention that quantum communication systems are already available in commercial systems, and I'll show some of those at the end of the talk. So now to quantum computing systems. There are a number of implementations which are being investigated in the United States and in other laboratories around the world. The first demonstration of quantum computing was in a molecular system using magnetic resonance techniques to probe the spin states of individual nuclei on molecules. This actually demonstrated operations on up to 7 quantum bits, which were 7 separate nuclei in a molecule. These measurements were done in a collaboration between IBM and MIT some 10 years ago. The problem with this technology is that it's not scalable to many quubits needed to perform useful functions. Perhaps without any doubt, the leading technology at the moment for quantum computing is ion trap technology. This actually uses the technologies that's been developed for atomic clocks, trapping individual ions and manipulating them with laser pulses. This is an image of a number of cesium ions which are trapped in an electromagnetic trap and can be accessed via laser beams. And by controlling the internal quantum levels of those ions and interacting them through centre of mass motion, it's possible to perform operations of order 10 qubits now. And leaders in this work are at NIST here in the United States. Now, one very attractive technology for quantum computing would be if we can get quantum computing into a solid-state system to make use of microfabrication technologies. This image down here is an image of a superconducting circuit which is able to effectively do quantum computing in the solid state, and groups now, in a number of groups, both here in the United States and in Japan, have been able to demonstrate quantum operations on both 1 and 2 quantum bit systems, and they're currently scaling this up to more. The final example on this slide is photon-based quantum computing. And individual photons are excellent ways to store quantum information just in the polarization vector of the photon, either horizontal or vertical. And one of the great benefits of optical quantum computing is that the photons can remain coherent, not be disturbed over the time of the computation. So I'd now like to focus on the research that's going on in our Australian Research Centre, and our centre has some very strong linkages to the US. As I mentioned, we've been funded through Army Research Office and National Security Agency and IARPA dating back to 1999 on two main projects that we're focusing on. The first one is a silicon-based scheme in which individual phosphorus atoms are embedded into a silicon host semiconductor integrated circuit. And so effectively you can think of each one of those phosphorus atoms as being one of the transistors in our quantum computer. So this obviously requires very advanced nanotechnologies, which I'll come to in a moment. The other technology that we're working on is based on single photons, where we can perform operations by passing the photons through beam splitters or through optical fibers and so on. One of the reasons that we're interested in this is by bringing together solid-state systems and photonic systems, we can actually combine the communications, the secure communications available through quantum cryptography with the computing in order to ultimately, in some decades, dream of having a quantum internet in which high-powered computations can be performed and then information securely transferred between various sites. Our centre in Australia has around 170 researchers. We also have now very strong linkages to the US, in particular to Sandia National Laboratory. We've just signed a cooperative research and development agreement to transfer some of our laboratory technologies into foundry capability that they have in their Mesa fabrication lab. This just shows a number of the fabrication technologies required. This one is some of our labs in Sydney, electron beam lithography and ion implantation. This ion implanter is used to implant the individual phosphorus atoms into our qubit chips. But I'd like to spend a little bit more time on this technology, which is a bottom-up assembly approach, in which a scanning tunneling microscope can be used to perform lithography to position individual phosphorus dopants. What we see here is the surface of a silicon crystal, which is coated in hydrogen. This STM tip can be scanned to remove the hydrogen, opening windows for phosphorus atoms to be positioned. Here, individual hydrogen atoms on the surface of the silicon have been removed in order to allow us to position individual phosphorus dopants. And using this technology, we're able to make individual atomic structures. This is just a brief video showing our STM tip scanning into the centre of one of our devices. The marks you can see are registration marks, which allow us to subsequently identify where the individual atoms are and to make electrical connections to those devices. The image on the right is the scanned image. This is showing now a variety of devices that are fabricated using the STM. These are quantum wires, and our group in Sydney, led by Michelle Simmons, has been able to demonstrate conducting quantum wires, phosphorus quantum wires, with widths of only 2 nanometers. So anyone familiar with the electronics industry appreciates the significance of that length scale. Our group's also been able to, using ion implantation, fabricate devices. This is a silicon single electron transistor that we've developed, and buried under here are individual phosphorus atoms, and we're able to observe an electron being moved from a phosphorus atom into this single electron transistor. We've also made a variety of other single atom transistors. This is a gate used to produce a tunnel barrier in a MOSFET, and this is just data obtained when there are no atoms implanted. If we now implant 3 phosphorus atoms into the structure, we find in the transport characteristics the characteristic signatures of the individual atoms, and so we're actually tunneling through those individual atoms. If I take a trace along here, this is measuring the current through the transistor as a function of the control gate voltage, and these sharp peaks correspond to tunneling through those individual phosphorus atomic levels. If I focus in further here, what we find is that the lower level, in the presence of a magnetic field, shows the characteristics of a spin-down electron, while for this state here, in a magnetic field, the energy increases for that transition, indicating that this electron is spin-up. So in these atomic transistors, we've for the first time been able to, in an engineered device, probe the individual spin states of individual atoms, which is essential for the ultimate realization of the quantum computer. So in our optical programs, we've demonstrated a number of quantum operations, the CNOT gate, and more recently have actually demonstrated the Shor factoring algorithm on a very simple number, just dividing 15 into its components of 3 and 5. And in a collaboration with the University of Bristol, we've also demonstrated a basic quantum operation called the CNOT gate in an integrated optics system, and using some of the types of technologies that Evelyn Hu presented this morning. So just jumping to those applications, as promised, here's an example of an available commercial system, quantum communication system. This one is produced by Magic, which is headquartered in Boston. Another company in Switzerland is also providing local area networks. And the challenge in quantum communication systems at the moment is to develop quantum repeaters that can allow us to go from a 100-kilometre transition all the way to into continental transmissions. I've already mentioned the importance of factoring. This is a key application, obviously, of interest to our security agencies, and high-performance computing. At the moment, quantum computers, or at least quantum algorithms, have been shown to have a number of applications, for example, the code breaking, but simulation of physical systems is another important one, and we believe that when these powerful computers are developed on the timescale of 15 to 30 years, that they'll be absolutely essential for advanced modelling of physical systems. Also, some of the technologies I showed you, the single atom fabrication technologies, we believe will be very important in developing understanding of conventional integrated circuits over the next 20-year period before quantum computers are developed. So what groups are doing this around the world? Well, in addition to our team at various universities in Australia, we have a number of, this is our own centres, links to various labs in the US. I already mentioned Sandia, but we've got interactions with Harvard, Wisconsin, Lawrence Berkeley labs, and a number of others, as well as a number of groups in Europe. This shows the total groups around the world that are involved in this work. You can see now a number of groups springing up in Asia working on quantum computing. The total investment, to give you an idea of scale, is still small. This is because of the long-term nature of the project, a total of just under 200 million per annum. So I'd like to finish, if I can beg another couple of minutes, by showing a brief video of a visualization of what a quantum computer of the future might look like. If we can switch the video, please. This video is actually developed by some researchers in our centre together with people at the University of Calgary, and was funded through the Army Research Office and the National Security Agency here in the US. So beginning here is just summarising one of the main applications, which is to factor a large composite number for code breaking applications. This is a visualisation of the silicon chip that would be on some motherboard, and now showing the quantum componentry. So the important thing about a silicon quantum computer is that the chip can actually be used on a conventional motherboard. It will require cryogenic cooling, but besides that it effectively would look like any other silicon chip. We're now zooming in to look at the individual phosphorus atoms. So each one of those yellow dots represents, in fact, a silicon atom in the lattice. The phosphorus atom is the bright spot in the middle, and what you see buzzing around it is the wave function, or the probability density, of a single electron around that phosphorus donor atom. The graphic at the top right shows it's what's known in the field as the block sphere, which shows the angular momentum of that electron. And by performing various operations, we control the angular momentum or the spin, and this is how we perform single quantum bit operations. You're now seeing an electric field being applied to distort the electron cloud around the donor, and by doing this, the interaction between the electron in the cloud and the spin on the nucleus at the centre can be controlled. That interaction between the electron and the nucleus is known as the hyperfine interaction, and anyone involved in magnetic resonance will be very familiar with that interaction. And this is the way that we're able to control those single spins by changing that hyperfine interaction and tuning to it by the use of the surface gates. You're now seeing two nearby donors with their electron clouds on them being manipulated by surface electrodes on the surface of the silicon chip in order to interact the two electron clouds, and in this way 2 qubit operations can be performed. This is using the electron exchange interaction, for those of you who are familiar with that principle. We're now zooming out to look at an array of donors. These will be fabricated, for example, using that STM approach to create large arrays of high precision atoms. The donors are arranged in lines, or at least in pairs of lines, in order to allow communication between the donor sites. On the left, we see a reservoir of atoms. This is a large grouping, which is where the readout occurs. And now, this particular vision, which is actually based on a detailed scheme that's been developed by one of our workers at the University of Melbourne in our centre to allow fault-tolerant error correction of the quantum computing codes. What you're seeing there is groups of 14 electrons which are being manipulated, and those 14 electrons store one logical piece of information that has inbuilt error correction. Zooming out, we see the conventional circuitry that is used to pulse and control the gates on the chip. And just finishing here is now each one of those arrays of bits will be able to store parallel states, and one of those parallel states will be available to ultimately crack the encryption code that we're trying to search for. So with that, I'll let the credits roll, and thank you again for your attention.